Hello students, we're on notes number 31 today and we're moving into chapter 4 and we're still kind of in the area of the course that we would call applications of derivatives, but rather than having a word problem or a story problem kind of application, it's more like applying these concepts to graphs. So you're going to see a lot more ideas tied together about graphs and derivatives as we go through the next few lessons. So notes 31, the word is extrema. That would be plural for extremum, and extremum would be a maximum or a minimum. Plural would be maxima and minima. But if you mess up and you say maximums and minimums and extremums, it's okay. All right, so it would be a really good idea to read the section in your book, which starts on page 215. And goes to the top half of 220, just to get a little bit more information. So I'm going to be summarizing that information in our notes today. And chances are I'll break this up into 2 videos. So there are 2 kinds of extrema. Local, which are also known as relative. Sometimes I use one word, sometimes I use the other. And absolute, which are also known as global. A local maximum could be defined kind of casually as no point in the neighborhood is higher. So I like to avoid saying that it's the highest point because there actually could be a tie for the highest point, or you could have infinitely many points together at the same height, making a horizontal line, but no point is higher. And then what's the neighborhood? That's not well defined. So points in the area. That area could be infinitely small and it's still a neighborhood. Okay, so to the left and to the right, and no matter how small of an interval you want, no point is higher, and it's a local maximum. Similarly, a local minimum we could describe as no point in the neighborhood is lower. We usually think of it as the lowest, but again, it could be tied for the lowest with other points nearby, so we'll just say no point is lower. So local or relative has to do with the immediate neighborhood, whereas absolute or global has to do with the entire domain or the entire interval that's designated or the entire graph. So for an absolute maximum, no point is higher. For an absolute minimum, no point is lower over the entire thing, not just over the neighborhood. So let's take a look at some examples. So here's a graph. And we have a closed interval from A to T, and we're going to look at each of the numbers A, B, C, D, etc., and state whether there's a absolute maximum, an absolute minimum, a local maximum, a local minimum, or neither at that point. And notice that I have some shortcut notation there. So capital M for maximum, lowercase m for minimum, A for absolute, L for local. All right, let's work on the local or relative maxes and mins first. So find a point where in its neighborhood no point is higher. That would be like here at B. So that is a local maximum. Another point that has a neighborhood where no point is higher would be here at E. That's a local maximum. Notice there are a couple of points that in their neighborhood no point is lower. So D, that's kind of roughly D, hard to tell exactly where. Local minimum, and also S, local minimum. Okay. Now, for the absolute maximum and absolute minimum on this interval, which point has no other points higher on the entire interval? That would be happening at B. So that's also an absolute maximum. And where do we find our lowest point and no other points are lower? That's happening at D. So that would be the absolute minimum. So a point can be both an absolute and a local extremum at the same time. Okay. You can only have one absolute maximum y value, and one absolute minimum y value on an interval, although it could happen at more than one x value. If you had a horizontal line segment right here, where every point there was that height, then all infinitely many of those points would be at the absolute maximum. Okay, what's happening at point A? Well, it's kind of like the end of a cul-de-sac where it only has, or maybe a dead end, it only has a neighborhood on one side and not the other. So we don't include that in terms of local maxes or mins. So we don't call the end point a local minimum, even though on the one side of the neighborhood, every other point is higher, no point is lower. So we're just going to say that's neither. And the same is true for the other end point at T. So that's neither. So what about what's happening at C? It's not a maximum or a minimum, so it's neither. And the same thing goes for R. Now, actually, those points do have significance, but we haven't talked about concavity, concave up and concave down. So we don't have a word for that type of point yet, but that's coming in a few lessons. Okay, here's another example. So why don't you pause and give this a try, doing the exact same thing we did on the last one. And then you can resume the video and we'll see if we agree. Okay, so I'm going to look for local maxima, and that would be at E, at S, and I'm going to look for local minima. That would be at B, also at C, also at D, and at R. And that horizontal line segment can be confusing to people, but remember the definition, no point is lower. So you have infinitely many points at the same low height. They all get to be included as a local minimum. Okay, let's go for absolute extrema. So where do we have the highest y value and no y value is higher? That's happening at E. Where do we have the lowest y value and no y value is lower? That's happening at T. So that would be the absolute minimum. Okay, once again, we have an endpoint here at A that's not anything. And what are we missing? We've labeled everything else. So we're good. Okay, now, there's a difference between what is the maximum value and where is the maximum value. If you're asked where is the maximum or minimum value, you're looking for the x-coordinate of the point. But if you're asked what is the maximum or minimum value, you're looking for the y-coordinate of the point. Number 3, use the graph to state the absolute and local maximum and minimum values of the function. In other words, what are the absolute and local maximum and minimum values? So we're going for y-coordinates. Okay, so for this first one, if you need to, you can pause and make a sketch. Absolute maximum, absolute minimum. Okay, highest y value we see is 4. So the absolute maximum is 4. The lowest y value we see is 0. So that's the absolute minimum. Local maxima. Here, at a height of 4, that point has no other point higher in its neighborhood. And here, at x equals 6, we have a height of 3 and no point is higher. So 3 and 4 are local maximum values. And local minimum values, here we have a point at a height of 1 and in its neighborhood no point is lower. And here we have a point at a height of 2 and in its neighborhood no point is lower. So local minimum values at 1 and 2. Now you can pause and work through the next one and then compare the answers. Okay, once again, looking for the absolute maximum. So the very highest y value we have here is 5. And absolute minimum, the lowest y value we have here is 0. Local maxima, we have several. We have something at a height of 2, something at a height of 3, and something at a height of 4. And local minima, we have several. Something at a height of 0, something at a height of 2, and something at a height of 1. 0, 1, and 2. Okay. So next we're going to explore a little bit something that's going to lead us to a theorem. So I have 4 different scenarios here. I have a graph on a closed interval. The closed interval is from -3 to 3. Notice that this is not continuous. We have this discontinuity at x equals 1, so it's not continuous at x equals 1. Does this graph have a global or absolute maximum? Well, notice that it's coming up toward a height of 2. Because of the open circle, it doesn't reach a height of 2, but it gets infinitely close. So there's no way to describe a number that's almost but not exactly 2. So no, there's no global maximum. Does this graph have a global minimum? Yeah, it reaches this closed circle here, which is at a height of -3, so yes, it does. So here's an example of a graph that does not have both extrema, both absolute extrema. It is on a closed interval, but it's not continuous. Let's look at the next one going to the right. Again, we have the closed interval from -3 to 3. Again, it's not continuous at x equals 1. Does this one have an absolute or global maximum? Actually, it does. It has a closed circle here. It reaches a height of 2. Does it have a global minimum? It does. It has a closed circle here and reaches a height of -3. So you could have a graph that's on a closed interval and is not continuous and does have both absolute extrema. Sometimes no, sometimes yes. Now suppose it's not a closed interval. So taking a look at this third one, we have an open interval from -3 to 3. We actually have something that's continuous on an open interval. Does it have an absolute or global maximum? Well, no, because of the open circle, again, you get closer and closer to a height of 2, but you don't actually reach it. So there's no finite number that describes the highest point. Similarly, there's no finite number that describes the lowest point. So you can have something that's continuous, but it may not have absolute extrema. The next one also is on the same open interval. It's continuous. Does it have a point with a maximum height? Look here. This point here is not an endpoint. That's fine. It has a height of 2 and no other points are higher. And then, okay, does it have an absolute or global minimum? Well, notice that you have a point at a height of -1 and no point is lower. So yes, again. So from these two examples, we see that if you have an open interval, even if something is continuous, you may or may not have global extrema. So the point of these 4 problems is to determine what are the conditions that must be met in order to guarantee global extrema. And if we put all these together, you have to have a closed interval and you have to have continuity. So that leads us to a theorem. It's called the extreme value theorem. It's an example of an existence theorem. In calculus, we have a lot of existence theorems. It tells you that something exists. It doesn't tell you how to find it. Global extrema are not guaranteed unless the interval is closed and the function is continuous. Now, there is a more mathematical, symbolical way to write, symbolical, is that a word? Symbolic might sound better, to write this theorem, but I think this will do the job for us, this casual wording. If your interval is closed and your function is continuous, you're guaranteed absolute extrema, an absolute max and an absolute min. If both of these conditions are not met, if one or the other is not met, or both, you're not guaranteed absolute extrema. Okay, that's where I'm going to end video 1. And then in video 2, we're going to talk about critical points and how we actually find absolute extrema. Thanks.